Okay, this is Chem 111. This is chapter 14. This lecture guide's up on Blackboard for you. Before this in the lecture guide, there is a periodic chart that you can use for your reference. We're going to talk about kinetics. And kinetics is a study of how fast chemical reactions occur. There are four basic factors that affect those reaction rates. Now, this is a measure of how fast they occur, not whether or not they will occur. That's more of a discussion for thermodynamics, which we'll talk about later on in the semester. So this is just how fast they occur. It could be that the rate is too slow to bother with and maybe just as good as not happening, but that's not the discussion we're having. We're talking about rate of reaction. We want to know about the reactant concentration. That is, higher concentrations tend to produce higher reaction rates because reactants can get together. The temperature, the molecules are bumping around faster, higher energy, more likely to get over those energy barriers for reactions. So increased temperature in general is increased rate of reaction. We can talk about action of catalysts. Catalysts are there to specifically speed up the reaction. And so they will usually by providing an alternate mechanism that's a lower energy pathway. If you had something that slows down a reaction, we call that an inhibitor, and that's kind of not what we're doing right here, but it works on the same basic premise. Surface area. If something's more finely divided, or the reactants can interact over a larger surface area, or they're able to be mixed together, all of those types of things are going to increase reaction rate. The goal being to understand things at the molecular level. So we want to talk about factors, and we'll talk about them each specifically, the first two more so than the second two, but we'll talk about all of them. We want to talk about how we measure what rate is, and then we can talk about whether or not it changes. So the speed of reaction is measured in the change in concentration over time. That can be a reactant, that could be a product. You need to pick one. So if we, for example, picked B, the average rate is the change in the number of moles of B over the change in time, or written delta moles of B over delta time. Alternately, we could use concentration since if the volume is constant, which we often will. So let's say we start with 1 mole of A and no B. And so here's our progress. If we represent at that time 0, so time t equals 0, it refers to the initial time, and we see that it contains a bunch of red spheres at 0 time, and the red represents A. After 20 minutes, you can see the blue spheres have grown in. There's less red spheres, meaning that there's more B growing in, which is blue, and less red, which is A. After 40 minutes, you see the blue spheres have grown in, indicating even more B is formed, and the red spheres, which is A, is diminished further. And we can try to quantify that in terms of calculating the rate. So if we say at time t equals 0, 1 mole of A, 100 red spheres with no B present. After 20 minutes, we say that there's 54 red spheres, so 0.54 moles of A, and the remainder 0.46 moles is B. After 40 minutes, there's 0.3 moles of A, 0.7 moles of B. So we can, let's say we want to calculate the average rate over the first 20 minutes. And we'll do that using A. So change in moles of A over change in time. So we'll look at the moles of A left at 20 minutes minus the moles of A at our initial time, t equals 0, and then 20 minutes minus 0 since we're looking at the initial versus the 20 minutes. So plugging in 0.5 moles of A we said was at 20 minus 1 mole initially divided by 20 minutes. That would give us a negative 0.023 moles per minute reaction rate for the reactant A. Notice it's negative, and it's because A is being consumed over time. A product would end up having a positive rate if you're looking at the rate of appearance or disappearance. So there's really two ways. I could look at the speed at which the products appear, change in moles of B over time, or the speed at which the reactants disappear, the change in moles of A per unit time. And there's really no right or wrong answer there. Experimentally speaking, we'd likely pick the one that's more easily measured. Hey, maybe there's a nice color change or something that I can see where I can measure that. Or I've got some device that can measure that easily. That's probably the one I'm going to pick. So if we do a plot where reactants A disappear and products B, which are blue, appear, we get a graph that looks something like this. You can see the reaction rate starts off a little faster and then peters off as the concentration of the reactant diminishes. And that is pretty typical. So we can see the A disappear and the B grow in. A lot of times it's useful to look at molarity instead of moles, which is often what we will in fact do. And we can do that since molarity in moles is directly proportional at constant volume. Let's look at a reaction of chlorobutane reacting with water to produce butyl alcohol and HCl. Now, we can look at the rate of any of those things growing in or disappearing. And so if we want to look at it, we're going to look at the reactant disappearing, and here is some rate data. Initially, we're talking about 0.1 moles of the chlorobutane. We look at it after 50 seconds, it's 0.0905 at a rate of 1.90 times 10 to the negative fourth moles per liter per second, or molarity per second. But you can see as the concentration diminishes, we can see that the rate also diminishes if you look at that last column, proving our point that if as the reactant is consumed, lower and lower concentrations, less likely to get together with what it needs, the reaction rate is going to proportionately slow. After some long amount of time, we'd say the reaction is gone, at which point the reaction would stop. So we can calculate the average rate in terms of disappearance of the chlorobutane, and the units for the average rate would be in moles per liter per second or molarity per second. The average rate decreases with time, as we mentioned, that, and if we plot that, we can get the instantaneous rate being the slope of the line tangent to the curve. The instantaneous rate is different from the average rate, and we usually call the instantaneous rate, that is the rate right now, the rate, although the rate over some range of time is probably a bit easier to measure, at least initially, until you can get a graph going. You really need to get a graph almost going to get an instantaneous rate in many cases. But if you're taking calculus, the slope of the line drawn tangent to the curve should sound familiar because that is the derivative. So if we look at concentration of the chlorobutane versus time in seconds, but focus on the graph and the lines drawn tangent, you can see the line drawn tangent initially is a much steeper curve than the line drawn later on. And that confirms what we were saying, that the reaction rate slows as the amount of reactant diminishes. So if we continue looking at the chlorobutane reacting with water, produce butyl alcohol and hydrochloric acid, what we know is that we could express the rate as the negative of the change in the concentration of the chlorobutane over time, or the positive, the change in the butyl alcohol over time. The only difference is, since they have the same stoichiometric coefficient, is that one's being consumed and one's being formed, therefore the negative sign. And so we have to end up divesting the measured rate from the means we use to measure it. So we need to be able to get the same number for the rate, regardless of which reactant or product I choose to actually calculate that. Because I don't want to get a different answer just because I pick an experimentally convenient reactant or product. I need to get the same answer regardless of what I pick. So if we look for a generic reaction where A reacts with B to form C and D, where the lowercase letters are the stoichiometric coefficients and the uppercase letters are the reaction products, we would say the rate is equal to negative A, or negative 1 over A times the concentration change of A over change in time, negative 1 over B, change of concentration in B over time, or positive 1 over C, change in C over time, positive 1 over D, change in D over time. And what you're looking at is you've got to factor out whether the coefficients are different, whether the reactants are products. So if you divide by the coefficient, flip the sign if they're reactants, you'll get the same answer no matter what you pick. And so putting that forward into a particular problem, let's look at the combustion of butane. 2-butane gas reacts with 13 oxygen gas to produce 8 moles of carbon dioxide and 10 moles of water vapor. The rate at which the butane is being consumed, there we're giving it a negative because it's being consumed, negative 0.20 moles per liter per second. Those negative ones mean they're in the denominator, so that'd be moles per liter per second. Sometimes they do that in line in a sentence, so just be wary of that. What is the rate at which the oxygen is being consumed? That is the other reactant, and in which each product is being formed, and then we'll get the overall rate of the reaction so you can see that it's independent of what you choose. And so if this is the rate the butane is being consumed, what about the oxygen? So the rate for the O2, I'm going to have to do a little stoichiometry. So I'm going to say negative 0.20 moles per liter per second of butane. And we're going to have 2 moles of C4H10 to 13 moles of O2. And so to get the rate of the disappearance of the O2, it's a matter of stoichiometry. It'll also be negative because it's a reactant, and so it'll be negative 1.3 moles of oxygen now per liter per second. And so that's one of our answers. Now we want to get it for each product. The rate for the CO2 now, you're going to flip the sign because it's a product. 0.20 moles per liter per second. 2 moles C4H10 to 8 moles of O2. We can do a little bit of canceling there. And so we're going to multiply that by 4. So we're going to get a positive 0.80 moles of CO2 per liter per second. Here, normally I wouldn't draw the positive sign explicitly, but I'm doing that for emphasis in this case because we got to, I want to distinguish it from that case. So lastly, the rate of the H2O, still positive 0.20 moles per liter per second. We're going to have 2 moles of the butane again to 10 moles of the H2O. Again, we're going to cancel, end up with 5. And so we're going to end up with 1.0 moles per liter per second. And again, positive. Now, that is the rate with respect to each reactant and product. What's the rate of the reaction? We end up stripping the stoichiometry out of it. I'll use RxN as an abbreviation for the reaction. We strip that stoichiometry, so we're going to say plus 0.20 moles per liter per second, but we're going to divide by 2, and you could do the same thing with any of them, but the rate of the reaction as a whole would be reported as 0.1 moles per liter per second. And then we would have to adjust it if we wanted a particular reactant or product.